Okay, so my name is Maximiliano Lopez, and I will be doing the question number 1 with dataset 2, and this is my final exam. So instruction says to analysis data in table number 1, then update data in table number 2, and report in addition to the other items that I need to describe, and make a comparison between these two datasets. So I have here the two tables of the different data sets. So we can see here that we have two factors with two different levels, and we have 5 center points with different values each. So I will open a mini tab. And make the factorial design just as I explained before. We have two level factorial designs, two factors, and we have 5 center points. There are no replications, so we just have one block. And here in the options, I'll just read to my runs and we're good to go. So here in the response, 1, 3, 1, 2, 9.5, 10, 9.5, 10, and 10. Okay, so now we can analyze this factorial design. In the graphs, we include the normal and half normal for it to plot, and the 4 and 1 residuals. Okay, so in the coded coefficients table, we can see that the factor with the bigger effect is factor A with 1.5, and factor B and the interaction between AB is the same, minus 0.5. Here in our model summary, we have a very good standard deviation, I would say, 0.27. We have a pretty nice R squared and the R squared adjusted. Here in our analysis of variance, we can see that just our factor A remains significant, or factor B and the two-way interactions between A and B is above our significance level at 5%. Therefore, they are not significant for this model. Yeah, so we can see exactly that what I said previously in the normal plot, in the half normal plot. Just the A factor remains significant, and B and A and B remains non-significant, and they remain kind of close to 0. So I do not consider it to be like kind of an outlier, but definitely they could be closer. Here in the Pareto chart, we see the same. A remains significant and A and B don't. Here in our residuals plot for the response, we can see that the data is not normally distributed, and there is a lack of randomizations with our observations. So there are plenty options we can take from here. We can use, in case we had replications, we can use blocking to improve the randomizations, but this is not the case since we only have one replication. And now we can remove significant factors to see if the normalization of the data improves. And we can also apply a Box-Cox transformation. I would say since we have a pretty nice R squared and R squared adjusted, we could just consider in improving the normalization of the data and the residuals. So I will apply first the Box-Cox transformation. Okay, so we need to have considered it to be reasonable to have -5 in lambda for the transformation. And now we can see that the effects between A and B and the factor B are significant, and or standard deviation improved, R squared and R squared adjusted improved. They are practically 100%. And now all of our factors in A and B are significant. But yeah, we can see that as well in the normal part of probability plot and the half normal. The Pareto plot shows the same, but we have no improvement in the normal probability plot in the randomization of the data. Therefore, although they become significant, that was not what I was aiming for. I was aiming for improving the normalization and the randomization. So I would take step number 2 from here, that is to remove non-significant factors. So I will first remove B, and if that is not enough to improve the residuals, I will then remove AB. Okay, so we can see here that the randomization improved a little and the normalization of the data too, but still I can see grouping here, and I don't think it's still a normalized data. So I will proceed to remove AB. We still have a quite nice R squared and a quite nice standard deviation. So we can see here that we just have our factor A, the only factor that is significant, and we can see now that the normalization of the data improved. It is more fitted to this line, and I think there's not a lot to say about the randomization. But yeah, I consider this to be a quite good result now. That we just have factor A to be significant. So I will run now I say a factorial plot to see at which level does A yields a higher response. Okay, so we can see here that the you say the great response are yeah, its bigger response is a mean of 2.5 at level 1, and the lower is at the lower level in -1. That will be 60 for factor A. Now, with these results, we can run a pair analysis. So we have a 2-level factorial design. We have 2-factor with 4 corner points, 1 replicate. The only effect that we have is 1.5. Number of center points per block, we have 5 center points, and our standard deviation is 0.3655148. Sorry, and we removed two terms. And since the curvature remained significant, I will include the center points for the model. Okay, so we can see here that we have a quite nice a power at 0.92. I consider it to be a very good power for this analysis. So we can now go with our second table, and in order to compare the results. So we can see here now that we have more center points, but they're not zero. They have a different level at 1.41. So for this analysis, we cannot run a factorial design like we did in the last table. We have to run a response surface design. Therefore, I will create it now. We have two factors design. We have custom and five blocks, no, 5 blocks. Yeah, our default alpha at 1.41. And okay, yeah, so we're good to go. Just let me remove the randomized runs. And we have now exactly the table we have or in our Excel file. So I will proceed just to enter the data. Okay. Yeah, so we're good to go and analyze this response surface design. For graphs, we will have the normal and half normal and 0.1. Okay, so now here in the coded coefficients table, we can see that our highest effect is AA with 4.837, and our lowest effect is 0.25. Yeah, so we have a nice standard deviation of 0.5, nice square R squared and R squared adjusted at 99%, 99 and 98%. So here in our analysis, we can see that as well as in the previous analysis, B and the two-way interaction between A and B are not significant. And I guess, okay, we have two unusual observations. And okay, in our normal plot, we can see that these effects are close to zero, so that's good. As I said previously, our AA interaction in BB are our highest effect interaction and most significant, I would say. So yeah, we can see that more clearly on our Pareto chart. In the AA, BB, and A interaction are the only ones that remain significant. And AB is the only one that, well, I mean, is B is non-significant too, but I will not remove it because the interaction between VB is more significant. Yeah. Analyzing our normal probability plot, we can see that our data is normally distributed. Not like the previous analysis, and the randomization seems to be quite nice. So I will now just remove the interaction between AB just to see if our R squared increases a little. Okay, so it remained practically the same, the R square adjusted, and yeah, so I think either this result or this result are a good result in order to proceed with the analysis. So I will now go and plot um, a factorial plot to see at which level does the factors yield a high response. We can now see here that at level 0 or our center points are where the response is higher. Now after this we can run a power analysis. Oh, okay, just let me use this data. Okay, so the same, we have two factors for corner points, one replication. The least significant, the lowest significant effect is 0.5, right? At yeah, 0.5 with factor A, and our standard deviation is 0.5039. We have 5 center points per block, and we removed one term from the model. Well, if we were to use the model where we removed one term, so we can see now that here we have a power of 0.14, that it's not considered a very good power. So yeah, I think that will conclude with the analysis of the data. I mean, in the previous table, we saw that after the plot, the the interaction between A and B and the factor B were not significant. Therefore, it just mattered the level on A, and it we saw that the higher the level on A, which was 80, well, the higher the response that it yielded. And in in our second table, we saw that in our interaction, yeah, just let me plot how you say a contour plot to see the interact, yeah. So yeah, as we can see, the higher response is yielded when B and A were in our center points, right? When there were 0 and 0. So when they were 70 and 50 respectively. But we don't have a quite nice power for this analysis.